So welcome back class to the course on applied computer vision, and last time in the classroom we discussed templates and then the starting of the edge detection methods. So I will go through it a little bit briefly and then we will continue with the details. So if you remember, we discussed that edge is very important. It can give us an idea about the picture or about the item in the image. So it is based on the important point is that edges, they are normally something steep inside the image. So steep things inside the image that give us the edges, like colors changing very quickly. So the basic idea for edge detection is that you look for a neighborhood or the area which has strong signs of change. But the main problems for this approach is what should be the size of the neighborhood and how to detect the change. So basically what we want to find out over here is when we go from 82 to 26, how we say that this is an edge. Similarly, from 82 to 33, this is an edge. Or from, so this is the x direction. What about this one? Y direction, 82 to this 33. Okay, so this is an edge. So going from high to low value or from low to high value, both are edges. So how to detect this? No, not this one. Sorry. So this one is not an edge. This one, 82 to 26. So these are the edges we want to find out. So we want to find out some sort of lining between the two areas of the image. So we discussed last time, edge is basically a place of rapid or fast change in the image intensity function. So remember, we are always doing like this in the class, that we take one line of image and we said that this one line, it represents the it is same as, it's equivalent to a signal. In signal processing courses you have done it. So signals, whatever they have the properties, same properties are of this one line of image R. So how to deal with this? So if you take a derivative of this image, so you will see that for this image, if you see, there is a white area. So white area has high intensity followed by low intensity and then again high intensity. So it has got two edges. One is from the white to black and the other one is from black to white. So basically white to black, it's shown over here. So you see this transition in the signal value. This is representing an edge. So to represent this, and what we can do is that one thing we can do is called as the first order derivative. So when we take the derivative of this signal, it will give us over here a negative derivative. So why negative? Because it is a transition from positive to from high to low value. Okay, so remember, when the signal value or when the function is decreasing, its slope is negative. So the rate of change is negative. When if the function value is increasing, its slope is positive. That's shown over here. So these edges, they correspond to some extrema of the derivative, the extreme point of the derivative. So basically what you can see over here, this is the extreme value of the edge. This extreme value represents the location somewhere in the middle of this transition over here. Clear? So remember, differential operators we discussed, we use them to detect the edges. So when we apply the differential operators, they give us the derivatives. So basically we model these operators as mask and or kernels. So since the start of the course we discussed that kernels, they are very important and we can use them for many different purposes. One of them, sometimes we use these kernels for image blurring. The basic purpose is not to blur the image. Blurring itself is not interesting, but the main thing is you want to filter the image. So when the high level details from the images are filtered out, the low level image components, they are blur. So that's what is happening, that sometimes we use masks or kernels to filter the images. Sometimes they are used to sharpen the images, and now we see another use, which is the differential or derivative with the help of kernels. So we discussed that there is something called thresholding. We will not consider for now. So what is gradient? We have already done this. This is all your revision for now, what you have done in the class. So remember, when we want to take a derivative, I discussed this thing very clearly, that normally the derivatives you study in your mathematics in your college somewhere, it is the d symbol x. That is called the derivative. Whereas this symbol over here, this is not a d. This symbol represents the partial derivative. So partial derivative, as most of you know, what does that mean? The partial derivative means that when we want to calculate a partial derivative with respect to x, it means that when we are recording, or we want to measure the change in x value, and at that time when we want to measure the change in x value, all other variables, they are kept constant. So let's say you have a function which has three variables, x, y, and z. So when I take the partial derivative of x, so for that purpose we keep the y and z constant. We don't disturb them. We keep them constant. And this makes our calculations simple. So a lot of the times it keeps the things very, very simple, and we can focus on the x component only. This is not the case with the derivatives, the normal derivatives, the other ones, d over dx, where the other components can also change, and that makes the things complex. Practically in the real life, this is normally the case, that all the variables, they are changing independently, they can change. But for us, we keep the things simple by using partial derivatives. So over here, we are considering the partial derivative of x. So we are only measuring the change in the x direction. This one over here, we are measuring the change only in the y direction. And if you want to measure the change overall in the image, so we measure the change in any direction as a sum of changes in x and y directions. So these changes, we record them, and their sum will give us change in overall in a two-dimensional image in any direction. Clear? So remember, for example, this is a vector that represents the change. So this vector, if you remember from your mathematics, that this vector or any vector, it is made up of two components, delta x and delta y. So this is maybe delta y, and this is the delta x. So any vector, it is made up of two components, x and y, and those two components we measure over here. So gradient points in the direction of most rapid increase of intensity. Here are some formulas given. For example, this gives the gradient of the image shown by the partial derivatives, but the gradient direction can also be calculated with the help of this tangent formula. We will not consider these much details for this course. Okay, but we can easily find the direction of the gradient and the strength of the gradient as strength. But for this course, we will try to keep the things simple. Our algorithms or CV2 will do this task for us. So what does, so there is a quiz, a small quiz. What does it mean when the magnitude of the image gradient is 0? We have discussed it already in the class. When gradient is 0, it means there is no change. So it means is that the image is constant in that neighborhood. That constant can be any value. Maybe it's the maximum value, maximum white color, constantly white. Or it can be a zero color, black, constantly black. I don't know. So it is a constant. It can be maximum, it can be minimum. So the right answer is D, which is all three of them can be true. Okay. So that is fine that we have seen till now some of the details from the calculus. We try to use it over here. So these courses from your final year are mostly they are using the mathematics and physics and other subjects that you study earlier. Here we are trying to use those courses in our practical applications. So this is what is happening over here. So discrete gradient, they show you the partial derivative, they take the discrete gradient, leave it. Leave these formulas, we are not interested. We have discussed this thing also in the class. So here you see a zebra. So it has got lines, and the lines you see over here, there are the gradient is taken. So I can just suppose, I don't know. So finite difference, which one is the gradient applied over here? If you see, this is just something related to the feeling. So in the class, normally the projector quality is not so good, but here on in the video, maybe you can feel it better. That these black lines over here, they are more prominent. You can easily feel them. Very, very clear. Whereas from going from down to up or up to down, these lines they are not so clear. So from this I can say that this is the derivative that is for the x direction. Clear? Some of you already questioned in the class, and the question is that still we are seeing some of the lines. Yes, we see these lines because these lines are not 100% parallel to the x-axis. So they are not perfectly smooth lines. That's why we see a little bit of the gradient or the derivative. That is only the x value of the original change. We don't record the y value of the change. And for your lab work, if you remember, and the chessboard example, you have seen over there that gradient change, when it is parallel to the x-axis, it is not detected at all, zero. Clear? Here is another example, partial derivatives that are taken for x and y. So this is just related to the feeling. And derivative, partial derivative with respect to x, it means that you will see more changes which are coming when you scan from left to right or right to left. Whereas the partial derivative for y, it is more related to scanning from top to bottom. Clear? So pause the video and look at it if you can feel those changes clearly yourself also. So the filter they have used over here, it's some sort of this filter, but we will see some more better filters. So we want to use the operator or the mask or kernel that we can apply to get the same results, and these are the operators that we will be using. So here you see one, so there are many kernels that you can use to get the desired result of having a derivative. So one of the examples is this kernel. This is a nice kernel, but it is not symmetric because there are only two values over here. You see, on this axis it's okay. So maybe there is a middle value and then the top and the bottom are zero. It's okay. But for the columns, there are only two columns, so it's not symmetric. So not a good thing. We have discussed already for many reasons. Symmetric kernels, symmetric images are preferred in computer vision in image processing. So here you see this is average of left and right and derivative, and here you see some sort of thing which is quite symmetric. This one is symmetric image. Clear? But we are not going to use these kernels. We will be using this. So I told you this is some error in the slide, so change it. This is SX and this is SY. Okay, So these are the kernels for one of the techniques. These are called Sobel operators. So this is Sobel X and this is Sobel Y. So you see over here, from minus to the plus side you go in X direction, and here you go from minus to the plus in Y direction up. Okay, so it gives you the two Sobel operators for gradient detection. So they have again given the formulas for gradient magnitude, or magnitude means the size or the value or the strength, and the other one formula is given for the tangent, for the angle of the gradient. But you don't need to memorize these formulas. So here are some of the results. So you see you have an original image, and you have then got the gradient magnitude and the gradient thresholded magnitude. Thresholding we haven't studied, and it's not so important. I think we will skip it. Not so important. So here you see the example. So there are many other field operators or kernels. One is Sobel, Privet, and then there is one called Roberts. So out of these, the Roberts is not symmetric. So remember, you have to keep in mind these things. Remember them for your exams also. Okay, and these are out of these three operators. The first two, Sobel and Privet, they are symmetric, whereas Roberts is not symmetric operator for gradient. Clear? So remember, if I suggest that take these operators in the lab, you will see there is an exercise also on this, that you have to apply these operators on the images to see the results, if you can feel any difference. So here is some MATLAB code. We just ignore it. We will be focusing on Python. So remember, to compute the gradients, you can use convolution and correlation. So which one? So what's the question? It's better to compute gradients using convolution, since that's the right way to model filtering, so you don't get flipped results. And correlation, because it's easier to know which way the derivatives are being computed. So what you think? So what's the question? The question is that over here you have got these operators. So if you take this operator, remember you are doing the same thing. You will take this operator and you have to apply it on the image. So how you apply it? So remember, always we apply the image, apply it on the image using correlation or convolution. So over here, what type of operator we will use? So the preferred one is the option B. We use correlation, because convolution at times, depending on the operator or the kernel, the image can be inverted. For convolution, image is inverted. For correlation, there is no inversion. So correlation is the perfect safe option for application on any type of kernels. Clear? Now some technical details. So till now we have seen that the images, till now we have seen that we want to get the derivative from the image. Practically what happens is that, let's say, so remember from the last many chapters, we take an example in signal processing, and then we apply some concepts on a signal, and then we use the same example and extend it to the images. So here you see an example of a small signal. So this is a small single row or column of image. So you can say it's just one line of image. So it's like a signal. But the important point about this signal is that it consists of, it's a noisy image. So here you see a large number of spikes on the image. So these over here show a little bit of fluctuation in the image value, in the signal value, and same is happening over there on the top. Now if you apply derivative for this signal, what will happen? You will get this result. So this result, this is a disaster. Can you find over here any edge? No, nothing. Why it happened so? Pause the video and think over it. Can you find it? Why? So the reason is that the noise over here, basically it is making fluctuations in the signal. So signal is going up or down. The derivative, the job of the derivative is to find out if there is a change in the signal value. It does not care if the change is too big or too small. So even if there is a little bit of change, the fluctuation because of the noise, the derivative will detect that change and it will show you that all of them, they are edges. So there are maybe thousands of edges over here. That's what is happening over here. So it's a disaster that's going on over here. So you see, when the noise is increased, and there is one lab task where I show this practically, that if there is a noisy image, so if you remember the images you have got for that lady Lena, so there is salt and pepper image and there is another Gaussian image, Gaussian noise image. Take those images and apply the Sobel operator on those images. What will happen? You will see the result. It will be something similar like the previous screen, this one. It will be something similar like this, and the result will be total disaster. Not good. So here you see, and here they are not showing so much good results, whereas in my lab notes it's much better, more clear. So here what they want to show is that there are these images, the main images on the top, these are the images, and below are the gradients, derivatives. So when we are increasing the noise in the image, what is happening is that the image gradient also has got lots of noise in it. But in our lab work it is more clear. I don't feel this one is much clearer. So what should be the solution? What to do? Again, pause the video, think over it, and then we discuss. So what happens is that the image, if it has got noise, it will give me a bad derivative, bad number of or bad representation of edges. So the best simple solution is to remove the noise from the image. That is what we were doing in past so many lectures. So remove the noise. So this is your original signal F, noisy signal, and you take a kernel. So this over here is a Gaussian kernel. If you remember, Gaussian kernel is basically a two-dimensional mountain. The original Gaussian kernel in signal processing, it's something like a bell-shaped curve you see over here. So this is the kernel. So when you apply this kernel on the image, what happens is, so when you do the correlation of H and F, what happens is that all this noise, it's gone, finished. There is no noise over here, but there is one more effect that happens around the edges. What happens is that the Gaussian kernel, it will make the edges more smoother. Before it was a steep curve, steep line, now it is more smoother. So noise is gone. Two things have happened. Number one, noise is gone. Number two, edges are now smoother, not so sharp. These two things have happened. Now if you apply derivative on this signal, this result, the result will give you the value, the peak value over here, which represents that this which represents the derivative value half high over this location, which shows that there is an edge at this location in the image, and that's true because this was an edge, if you remember. Is it clear? Again, if you people are not understanding any question, ask in the comments in WhatsApp group and we will discuss it again. Clear? You are also free to ask each other to do discussions in the group. You are welcome. So here what we have done. So we have done two major operations. We take image, we take the kernel, and we make the image smoother by taking the kernel, by applying the kernel, and then second operation we apply the partial derivative on the smooth image, on the blurred image. Clear? Shall we go next? So we did this, problem solved. So you look for the peak value that will give you the edge. So that's what is happening over here. Now one important thing, if you remember, we studied there are 6 or 7 properties of convolution. You saw somewhere, I think, in the exam also. So why I put it in the exam? Because it was important. We have to use it. So here it is, convolution. One of the properties of convolution is derivatives. So remember, a derivative property related to the signals, it says that if I am applying the partial derivative on some signals h, and then there is the correlation or convolution on f, and this is same as the derivative applied to one of them. So you can apply it on one of the signals, either f or h. The result will be same. Okay. Pause the video, look it carefully. You see the partial derivative applied on the h, but you can apply it on the f also. So let's say I write it other ways. So here h, and then there is a correlation or convolution symbol, and then partial derivative of sorry, this is not d, partial derivative with respect to x of f. So all these three equations, they are same, they have the same meaning. Okay, now this is very important point. Why we want to do this? What's the purpose? So here you see, the important point over here is that, so let me go back. The important point what we want to make over here, the important point is, you have a big image, maybe 1 million pixels, very big. Okay, f. You have a small image as compared to the real image, the h or the kernel is very small. How small? You already know, maybe it's 3 by 3. Whereas the image is normally very big. Maybe its dimension is in thousands, maybe 1000 by 500 or 1000 by 1200, but it's big. Comparatively, the image itself is bigger than the kernel. Now if you take the image and you convolve it with the filter to make it smooth, to remove the noise, then you will get a new result. So let's say the result is f prime. Clear? So that is your result. You have convolved them. And this is a smooth image. Now on this smooth image, you correlate with it a Sobel operator. Okay. So we correlate the Sobel operator with this. So Sobel operator, when you mix this Sobel operator with the f prime, what does it mean? It means that you are taking the derivative of the image. But this thing over here, what is happening is that how much computations you will make. So let's say your image size is n by n, and your kernel is 3 by 3, 9. So how many operations you make over here? 9n square. Okay, done. Here you have got another times you have the same image size. So remember, if that was f image, f prime is same size. So let's say it's also n multiplied by n size image. Okay, when you do the correlation with the Sobel operator, Sobel operator is again, let's for now we say that we only use one direction, x, we don't use y. And if I'm using one operator, so its dimension will be 3 by 3. It's a simple 3 by 3 matrix. So what is the size of this computation? 9. So 9n square again. So I'm doing these two computations 2 times, 9n square plus 9n square 2 times. Now see the second option. Let's take the derivative of the h only and then convolve it only once with f. What does this thing mean? So you take the derivative of h, it means that you have the h which is 3 by 3, and you convolve it with another matrix 3 by 3. So what do you say? How much time it will take? 9 computations multiplied by 9 computations, only 81 computations. And over there your answer was in millions maybe, or at least in thousands. So pause the video, think over these concepts, whatever we explain over here. Very important. The purpose of all this exercise is that this operation over here, it will take millions of computations. The one, this over here I have shown, this will also take millions of computations. Whereas the one that I show over here in the middle, this one, this will take very less number of computations. Why? Because it is taking the derivative of the kernel. And we are using the advantage of mathematics because all three of them are same things. So here what I am doing is I take the derivative of the mask of the kernel, and then this derived kernel I apply it on the image. So these together, this derived kernel, it will have computation size of 81. Then I take this 81 and I apply it on the original image, which is f. Clear? So this there is not enough space. Let me try to show it. So this is your h and this is your Sobel s. When you convolve them, you will have 9 by 9 computations. Result of these two images, these two kernels will be another kernel of same size. Size is not changing, 3 by 3. Now you apply this derived h on the image f, original f. So how many computations will happen? There were 81 over there, and now you will have over here how many? 9 multiplied by n square. N is the size of the image. So you have total of 81 plus 9n square as compared to the old approach where you had 9n square plus 9n square, which is too much because remember n square will be in millions. Pause the video, go through it, and if you have questions, ask me. So here is the result. You see, you have the original image, which is the noisy image f. You apply on this image the derived kernel h, the derivative of the kernel h. And so remember, derivative of the kernel, why we apply it? The reason is given here. Why I take the derivative of h? Because it's less computation intensive. Because the original approach is too much disaster. If the image is too big, it will take too much time on the computer processor. So here it is. This is your kernel h, and this is interesting. You see over here the derivative of the kernel h. It looks like this. Now pause it. Pause the video and think over it. Why it is like this? So you see over here, you have got h. it has increasing slope over here. So when the slope is increasing, remember the derivative will be positive. Okay, so somewhere in the middle the derivative will have the maximum value, but still it is positive. When you reach at the top, so remember when the slope becomes 0, derivative is 0. So top is represented by this location over here. Then what happens? We start descent, we go down. So going down the slope, that is represented by the negative. So that is represented by this half of the derivative. So basically this over here, it has got the derivative. This is the kernel h and this is the derivative. Now if you understand this thing, I have a question for you people all. This over here is the derivative of h. If I ask you to take another derivative of this, can you do this? What will be the image look like? Take another derivative of this image. What it will be? Please draw this and save it for yourself. I can't check it, but I will make it later on, and you should try to see if it is same. So when we apply this derived kernel h on the image f, it will give us this result, and the result is exactly the same as we have seen before, if you remember this thing. So derivative of h into f, it is same as this derivative of h convolved with f. Okay, so derivative applied on h only or together on both of them, it is giving the same result, but this thing over here, it is less computationally expensive. Clear? So I asked you people to draw the second derivative. So the second derivative, the result comes like this. Why it comes like this? Let me show you. So here it is. So remember the same rule. When the derivative, when the line is slope is positive, the derivative is increasing. When the derivative increases and on the top it reaches 0, and then what happens? It is going down. So it will keep on going, but when it reaches at this location, instead of finishing, because there is no stopping, it will keep on growing much further, so double. So if this length was 1, this will be at least double, 2. So it will keep on going and it will reach this point, negative, and here it will come back to 0. Till that point it will come back to 0, and then it will be again increasing. So in effect, it will give you something like this thing over here. The positive half will be smaller, whereas the negative half will be much bigger, because the negative change is together. And we normally call it inverted Chinese hat. So it's like a Chinese hat, but it's upside down. Clear? So when we apply, why we are doing this thing? What's the purpose? Why? So why I take the second derivative, that's another important point. So if you see, this is my result, the whole result. So for this result, if I take another derivative of this result, what will be the result? So what I will get from this result, if I take another derivative for this result, this positive half will give me a positive slope like this, and this negative half will give me another slope. Okay, now what is the purpose of taking the second derivative? This has something to do with the electronics, you can say, or signal processing. Remember, in signal processing in electronics, to detect the peak value of a signal, it's not so easy task. It's a difficult task to detect if a signal has reached its peak value. Whereas against this thing, opposite to this thing, It is very easy. There are circuits very easily created in electronics that can easily detect the signal's value transitioning from positive to negative. Why it is so? It's the discussion in electronics. You can check it over there, or you can ask any of your electronics course teachers that there are many circuits that can easily detect positive to negative or from negative to positive transition in the signal. So this is the only purpose why we take the second derivative, because at that place, if you see the previous slide, the edge was represented by a peak value, positive peak, but it's not easy to detect this positive peak. Whereas if I take the second derivative, now each peak, each edge is represented by a transition from plus to minus, and that's important, and that's very easy to detect. There are so many circuits available that can detect this transition in the signal value. So effectively, what's the summary? Summary is that we are going to use second derivative on the image. So practically we want to apply the second derivative on the product of H convolved with F, but practically this thing is same as this one. So I calculate it one time and I apply it all the times on the image. That is one of the advantages we saw previously. You see this thing? When you calculate the product of H and the Sobel operator one time, now this product you can use it on 1000 images. Same product. You don't have to change it. So this calculation you do one time and then you keep it, you save it, and you can apply it on different F values. Clear? For all the different types of F values, it will try and detect the edge from the image. Whereas in the other approach, if you are applying the derivative on the whole image, what will happen? Every time F changes, you will do the calculations again, which is very bad, very cost intensive. So this approach over here, it's good. It is saving a lot of computational cost. Clear? So how much we have done? Let's take a, let me check. So let's take a small break, and this lecture for now is enough for this much time.